Right, online. Good morning. You all hearing that? Right. So today we want to continue with Thermal. During the holidays, we finish up the laws and kinetic theory. Right. Before we move on, I'm gonna just ask a few questions quickly. Actually, we could do a quick Kahoot. On the Wi-Fi working, boy. And not working? Which one not working? Huh? The Wi-Fi working? All again it? Nathan? Yeah. If you're not working, just join with the person next to you. Right? You answer one question, he answer one question, right? Or like a team up. All right. So let's run over gas laws, which I think I gave all this one already, yeah, but it don't matter. It's the same topics that we're doing. All right. Let's run over the gas laws quickly. So log in here. And then after gas laws, we go back to that heading there, thermal quantities. Log in fast. Online, you all seen it, right? Log in quick as gas laws. You need a name. Who's that? Who's hot? Who's this? Change add a name to my please. That's starting, right? Yeah, let's start now. Alright, let's start, right? Everybody should be in. I think we are now getting there. Alright, hurry up. It might be a little delay there, so some people online. Right? So real bad. Some people get that wrong. Nah. Next one. Right, there's one rule I should remember from Connect. That's one thing I should remember from kinetic area. What's going on here? Upside down. What happened? Okay, just do it slow. I'm ready to go faster. Next one. Be careful, eh? Watch how they're looking back. No. I can't believe how they're looking back. They're looking back there. Huh? Very easy. Easy stuff all again. All again, it's easy. True or false? Huh? 8 people get this the wrong way. Upside down on top, boy. Annalie coming up there. Chloe, Aidan. Alright, so we still got one here. No more. Next two and first. Special. False. True. False or true? Right, so what happened here? 2 people get it wrong. Plenty little change. Or those who online really have the little lags. Next one, calculation time. Oh no. So the last one was a calculation. Everybody high up in the 4,000. Well, Chloe there. Upside down. Tion, Anya. Ashton, what's going on? Until you and Raj there. Last one. Spell it correctly, yeah? I'd add some more to this, some kind of lame kind of calculations. Finally, why everybody answer? Alright, so remember a little bit. Let me see. Chloe come third. Tion what? Tion come up second there. Way upside down win all yeah. Way upside down. Alright, nice, very good. Good job Annalie and Anya too. Raj jumped all of that. Alright. So that's one of the topics that we did over the holidays. Right? That's one of the topics that we did over the holidays, right? Today we're going something new. It's a new thermal quantity. Right? It's a new thermal quantity that we're going today. And the thermal quantity that we're going to do today is called specific heat capacity. I'm going to show you a quick little simulation of how it will look. But exactly what the name says, specific heat capacity, right? It gives you an idea, right? It gives you an idea of how much heat a substance could take before undergoing some kind of change, right? So let's take a look at this quick little simulation here. All right, so watch this here. If you look at the simulation here, right? We have two different materials. One has a large specific heat capacity at 20 degrees Celsius, and one has a small specific heat capacity at 20 degrees Celsius. And we're going to heat both of them, right? We're going to heat both of them, Ashton. And what's going to happen? Right? We're heating them for the same amount of time, and I'm going to stop it now. What you notice about the material with the small specific heat capacity has a higher temperature. See that? And the one with the larger specific heat capacity has a smaller increase in temperature. You're seeing that? So therefore, what does that mean? It means that the specific heat capacity gives you an idea of how much heat it will take before the temperature changes. So if you have a small heat capacity, it means that it will take a much smaller amount of heat energy for you to change temperature. That making sense? But if you have a large heat capacity, it means that it will take a lot more heat for your temperature to change. That's okay? Everybody okay with that? So that's the concept that we're going to look at, right? And while we write here, I can kind of give you an idea of what the relationship is. When they say specific, the size or the mass matters. So specific heat capacity, the symbol is small c, is the amount of heat energy required to change temperature of a particular mass. That symbol there is change in temperature. All right? So the higher your heat capacity, specific heat capacity, the more energy you need to change temperature. Are you okay with that? When you see heat capacity, you will see a big C. Common lowercase c is specific heat capacity, right? Uppercase C is heat capacity. And the formula is the same, except it's not specific to mass anymore, so you're leaving out mass. So you're going to look at two new quantities, Raj. Heat capacity and specific heat capacity. Are you okay with that? You'll understand what the quantity represents. Annalie? Follow what specific capacity means? No, it's not making sense? All right. So just take back a look at this example here. Right? Watch how this started, right? I was setting it. Same size, so same mass, clean up, same mass, same starting temperature. That's okay? But the difference between them is that one has a small specific capacity and one has a large, right? So what's going to happen after a while for running it? I'm going to run it for like a minute, right? Watch what will happen. Also, I'm not sure if you all seen it. If you all look, you all see that this, like the one with the smaller specific capacity, you all see the particles, like the energy transferring faster. You all see now? The energy transferring much faster. Look at the next one, right? You're only seeing like one particle red there. Here you're seeing a few more red. Here you're just seeing like one or two kind of red. That's okay? So the heat not transferring as fast. So a high heat, small heat capacity, heat transferring kind of fast. Here, it's not transferring that fast. Right. What should happen, Annalie? The heat for the same time, but this temperature is much larger than this temperature. So the smaller heat capacity, temperature change real fast. But the larger heat capacity, the temperature change much slower. Right? So that's the difference. Right? The large heat capacity can handle the heat, but the small can't handle it. That's okay? Online? Are you okay with that there? Nuria? Natalie? Natalia, I mean? You're okay with the concept of specific heat capacity? Yeah? Natalia, you okay? Right? So it's important that you understand the concept, because now we're going into the, in fact, before I go to the formula, what you say? That is specific heat capacity. What you'll recognize changing there as you apply the heat? What changing? Temperature, right? So as you apply the heat, temperature changing. Okay? So whenever you see C, whenever you see small c or specific heat capacity, I want you to always think of a temperature change. All right? Those are the small things I want you to memorize, right? Once you can remember that, it's easier for you to come up with the definition. All right? But what will happen? What else could happen? What else could happen if I apply heat? Anybody can tell me? What else could happen if I apply heat? If you apply heat, yes, temperature could change, but something else could also change. I'll use this one, eh? What else could change, Olia? The state, right? If I apply heat, After a while, it could change state. So what you say? We have ice at minus 20 degrees. What you graph? I'm going to apply heat to it. What you graph? It's still ice, and but as soon as the graph hits 0, start to melt. You recognize that? It changing state. While it changing state, it's staying horizontal, staying horizontal, staying horizontal. Now it's going to change temperature going up. You see now? Still heating, still heating. Temperature changing. Temperature changing. Still a liquid. But as soon as it crack 100, what's going to happen? It will start to phase change, and what will happen to the graph? It will start to horizontal plateau off. Watch it here. And evaporating. You see that? So on your graph, you might see this. You see a temperature change happening here. And a phase change happening here. You see that? Right? So there are two things you're going to learn about. Specific heat capacity that allows a temperature change, and specific latent heat that allows a phase change. Everything is heating up there. I want every glass to break. Nah. Right, let's see what will happen now. Just going on, going on. Oh, well, I thought the glass gonna crack by now. Okay, so those are the two quantities that we're going to look at today. In people who did the labs already, you may have experienced those two already in the lab. Right? So we have a definitions here. No need to write. Just write the formula for now, because I would like you to be able to calculate stuff with this, right? So specific heat capacity is defined as the amount of heat required to change the temperature of unit mass of a substance by 1 degree Celsius. That's the formula there. E is equal to mc delta theta. Write that down. Write it down and make sure you know what each quantity represents. Right? Write down, make sure you know what each quantity there represents, right? Please remember that we use this formula whenever something undergoes a temperature change. right, so that is for specific heat capacity. And then heat capacity, I said the difference between them. The difference between them is that it just don't have a mass, right? So write this here. And it's an uppercase C, right? Uppercase C. Uppercase C there, right? And next one. So all those have to do with temperature change. Oh, by the way, you can write a C. This is how big C, uppercase C, and lowercase c related, right? C is equal to MC. Right? Next one is the latent heat. That's for phase change. And look at it. That's for phase change. Right? So make a note right next to it that we're going to use this relationship here for a phase or a state change. Ready? Right? So let's see if we can apply this now, right? So let's take a look at a couple of cases and see if we can figure out which formula to use, right? And I want you to remember this. Top right-hand corner, I'm writing the three relationships, right? Two main relationships. E is equal to mc delta theta. This is the energy required for temperature change. And E is equal to mLh. This is the energy required for phase change. All right, so let's consider the first case. Suppose I gave you some water, a container of water. It has 2 kilograms of water, and we're heating it with some particular energy E. And the water went from a first temperature of 30 degrees Celsius to a new temperature of 70 degrees Celsius. Right? Atelier? Yeah? Yeah? Are you okay with it? You got 5? Yeah? Pay attention, please, Atelier. Right? And this water here has a specific heat capacity value of 4,200. Let's see if we can find the amount of energy needed to make this occur. Right? But look at the SI unit here, right? I can't squeeze it in there. Hold on. Hold up. Wait a minute. So your specific heat capacity is equal to 4,200 joules per kilogram per Kelvin. Right. How do we find E? So in order for us to find E, here's what you have to figure out. Did the water undergo a temperature change or a phase change? Underwent a temperature change. There was no phase change, right? So since it's temperature change, we're using the one on top. Everybody okay with that? Let's not wait. None of the rad should come back. Come back. Look like it went somewhere there. No? All right. So the energy required is mc delta theta. Everybody okay with that? Yeah? Right. So we know the formula now. E is equal to mc delta theta. Do we know the mass? Do we know the mass? Yes. Do we know specific heat capacity? Yep, it's water, right? Do we know the temperature change the water underwent? Yes. Right. But we have to line up. Well, I'm watching here, I'm watching the phone cell. I tell you, I want to take your phone, huh? Right? If you all watch here, you will see the SI unit as joules per kilogram per Kelvin. So is the mass in kilograms? Yep, 2 kilograms. So we're good to go. Temperature change. Is the temperature change in Kelvin? The answer is yes. Here's why. Here's why. If I were to change 30, oh, by the way, what's the temperature change in degrees Celsius? What is the temperature change in degrees Celsius? 70 minus 40, right? Correct? Sorry, 70 minus 30. So the answer is 40. Are you okay with that? In degrees Celsius. Right. What will be the temperature change in Kelvin? So here we're going to do. We're going to add 273 here, and we're going to add 273 here, and then minus them. Right? So when you work out this, you're going to get 343. And when you work out this, you're going to get 303. When you minus them, you're still going to get 40. You recognize that? Yeah, finally. So here's what that means. Yeah, Anya, here's what that means, right? The same temperature change in degrees Celsius is equal to the same temperature change in Kelvin. All right, so make a little note of that before you start to work this out. So the same temperature change in degrees Celsius is equal to the same temperature change in Kelvin. Maria, that makes sense? Hamlet, you listening? Nice, Hamlet. All right, what we got here? So let's work it out. So the mass is 2, the specific heat capacity is 4200, and the temperature changes 70 minus 30. How much you got there? So I don't understand the phase change formula on the left corner. Don't worry, I'm gonna show you that now. Right? We just working with the temperature change for now. The next example is phase change. Right, Chloe? I'll show you that now. Yeah. How much you all got there? 2 by 40, 200 by 7 by 40. How much you got? 336000. Yeah. So that's the amount of joules needed to change the temperature. Sure. Why are you doing that? Touch your phone. Beep, beep, pew. All right, so that's the way you use the formula for temperature change, right? Let's take a look at it for phase change now. Huh? Don't erase it. No. Go ahead and write it down. Right, so Chloe, so basically you use the formula based on what is happening to the substance. If the substance undergoing a temperature change, you use the one on top, the first one. If the substance changing state without temperature change, you use the second one. So I'm gonna show you that just now, right? Next one. All right, answer. So sometimes it questions simple phase to see if it's a temperature change or phase change. Sometimes it's more challenging, right? So sometimes I like to draw a little graph and see what happening. All right, I'll show you one that's now like that. Pardon? Or that SAC. Specific heat, yes, ma'am, that's a S. While you're typing on your phone, I'll write an S. SHC. Okay, so let's check this next one out here. Right, so let's take a look at substance number 2. Let's say instead of water, we have ice. So we have some ice here. We have 2 grams of ice, and we are applying heat. Right, that heat now took the ice at 0 degrees and turned it to water at 0 degrees. The temperature change? Temperature did not change, right? There was only a state change. So now, in order for us to find the E value, to find E, we're using M by latent heat. It's called latent heat of fusion because it went from liquid, it went from solid to liquid. So it's called LF. And of course, I'll give it the value, LF. Let's say it's 3.6. 3.6 joules per gram. Okay? So what do we need now to find the energy? What do we need, Carisha, to find the energy? The formula right there. What we need? We need mass and we need the latent heat. But you have to make sure that the mass is in, look at the unit, the mass must be in grams, right? So the mass is 2 and latent heat is 3.6. So we got 7.2 joules. Chloe, that makes sense? Yeah? All right, let's go again. No. Go ahead and write. But we're going again. But go ahead and write. But we're going again, right? Rush that. No, yes, yeah, moving slow. Okay, let's go again. Right. What would happen if it's a combination of things? What would happen if the ice melt and then when the ice became water, temperature increase? What you'll do in a case like that, Tion? If you had to guess. You had no choice. You had to guess. Why you doing a case like that? So the water was at zero, the ice at zero. You heat it and it melts. So during that melting phase, how you'll find the energy? What you will do? What the formula you'll use? ml, right? And then when it became water now, and it increased temperature, what you'll use then? MC delta theta, and then add up the values, right? So the energy now is, you have to sum it. You have to find the energy during the phase change and energy during the temperature change. All okay with that? So I'm going to show you any deep here now. So we have ice, and we're heating the ice. I want you to find E. So it went from 0 degrees ice to water at 0 degrees to water at 20 degrees. Right? I want you to find the total, use the same values. Specific heat capacity of water, that was 4,200 joules per kilogram per Kelvin. And I want you to use the latent heat as 3.6 joules per gram. And I am giving you 20 grams of ice. Let me see what you come up with. Take your time, break it up, right? So yeah, you have to find the energy here and then the energy here and then add it up. Try that fast. Actually, sleep here. Take your time, right? Right, so let's see how that runs out. Now I ask for the total energy, right? Total. So I'm gonna find E1 first. I'm working in red. So let's find E1 first. E1 is from ice to water, same temperature. So E1 is a phase change. So E1 is MLF. So that would be M, check the unit. L is in what? Grams, right? L is in grams. So I have to make sure I use grams. So it's 20 by 3.6, so that's 720. That's okay? 720 joules. Now E2. E2 is water going to water, and there's a temperature change. So we're using MC delta theta. Are you okay with that? Yeah? But here's the problem. Problem is what? The problem is grams, right? Our mass is in grams, but specific heat capacity is in kilograms. So I have to convert grams to kilograms. So that'll be 0.123, 0.02. That's okay? 0.02. Multiply by 4200, multiply by the temperature change, which is 20. Any questions? I convert the grams to kilograms, right? You can't convert this, don't convert that to grams, right? You convert this to kilograms. Multiply it out, divide by 1,000, 1, 2, 3, and then how much is that? Something good is happening today. 1680? 1680 joules. So now the total energy is 72 plus 1680. Anybody got that? Anybody got that? Yeah, look, Cleo got it. Cleo got it. Good job, Cleo. Are you okay with that? Tion? Ashton? You're almost there, Ashton. You're almost there. Don't want to take a seat. All right, so that's that. Let's make it a little bit harder now with some real values. Any questions online? Natalia? Aidan? Hamlet, it would be good if you could send me one answer, right? Right? Sometimes I could give you the energy, and you have to work backwards and find the C value or the L value. All right? But let's try this one here. Any questions, Olia? Raj, any questions? This one is for you, right? Something good. You have a calculator. You can use your phone. I'm sure you have your phone. You can use your phone. Or you can go online and get a calculator. All right. Something good is happening today. Beep 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 beep. Beep 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 beep. Beep beep beep. Beep beep beep. Something good. Oh, no. I'm not ready for that yet. Oh, I do what the second part is. All right, we have one little problem here, right? I'm not sure if all the values showing up. All right, here's it. Let's try this one. This has all the values. Copy this. Copy the last two values underneath. Copy down C and L. Sometimes you will see LF and sometimes you will see LV. LF is solid to liquid and V is liquid to gas. You'll see nada? Yeah, sure, I'll blow it up big and nice there, right? Something good is happening today. This one is for you, Raj. We got full marks here, Raj. Right, people who have labs, we try to, next week we'll try to meet and finish up the labs, right? Done all your labs already? So come they didn't finish. Say you finish. Huh? Oh, he went to the expo. You still have some to do. The electricity and oil labs. Huh? He doesn't understand that. Hey, we'll fix it up next week. All right, let's go. Try the first part here. Try the first part. Message your answers, right? I want to see your answer. Eden, Natalia. Pardon me, ma'am. No, same question, but you need those values. Go back to the values. So you didn't write down the values. So that's my fault. Write this down. That's a mistake, huh? There's a small mistake here. There should be kg. Kg. That's what it is. Kg. It's kg. Not k. Just kg. Okay? Hurry up. So we need those values. I can change it now. All right. All right. So let's try here. Try that in. Pay attention. If it's a temperature change or if it's a phase change. Hurry up. Work it out. Shh. Shh. Work it out. Go ahead. And the first part, just make sure you're doing the right thing. Well, what it underwent in the first part, Raj? What the substance underwent? A phase change of temperature change in part one. Temperature change, right? So what's the formula used to find the energy? Equals MC delta T. And you have all the values, right? Hurry up. All right, let's check out the first part. Nuria, don't forget to send your answers. Hamlet, I'm waiting on you first. We just waiting on Hamlet, right, Julia? Let's see what Hamlet came up with. And I am waiting on Natalia as well. Right, those who finish, what's your next part? Those who finish, do the next part one time. Water to steam. Take a pick and summon to Sean. Let's see what you have. Right, and then do the last part, and then I'll figure it right. I just waiting on Hamlet, it's on a value, right? Hamlet is still waiting, right? No, I just waiting on you, Hamlet. Take a pick and send it. Take a pick and send your work in. Can get the last part, yeah? Oh, let me show you the mark. 1 mark for that. One mark for the last part. 3 marks for the other 2 parts, right? That's a hint on what to do. All right, let's check it out. So I'll start it up here. Hamlet still didn't send anything. All right, Mr. Hamlet. I'll have a little talk with your parents. All right, so let's start here. Energy, temperature change. So that's MC delta theta. The mass is 1.5 and C was 4,200. Remember, you have to look at the units so you'll know if you're working in grams, kilograms, right? And the temperature change of the water is 70. How much you got there? How much? 441,000. Yeah, yeah. Part 2, they want to find same temperature, the different material, different states. So we're using E is equal to MLP. So 1.5 by, what was it? 3.6? Oh, 2.3 by 10 to the 6. And how much you got there? How much? 389? 389? 3.45 by 10 to the 6. Right, Chloe. Oh, you add it up after. 3.45 by 10 to the 6. Now, here's what is set after. But okay, 1 and 2. Here what is set after, right? The heat the water from 30 degrees to steam at 100. So what they did there is they combined part 1 and 2. You realize that? Right? So all you have to do to get the total energy for part 3, you just have to add part 1 and add part 2. So add 441,000 plus 345 by 10 to the 6. How much is that? 3 point? 3 point? How much shall I get? Just add them, right? And the little 1 mark, there was the hint as well. 3.891 by 10 to the 6 joules. Any questions earlier? Any questions online? Natalie? Natalia? Nuria? You all okay? Are you okay with this, Olia? Right? Next day, we're going to do the same thing, but we're just going to rearrange up a little bit. I'll give you the energy, and you'll tell me how to get C or how to get L. Naria, are you okay there? Natalia?